record to the call. Okay, so everyone, welcome for weekly seminar, and sorry for the delay. Today I'm going to have Brian McPeak from PISA tell us about error correcting codes and chiral CFTs at higher Genus. Please, Brian.
Okay, so sorry for the delay. And so today I'm going to be, and thank you to the organizers for inviting me. Today I'm going to be talking about some work that I've been doing over the past year with Johan Henriksen and Ashish Kakar. Johan's a postdoc with me at PISA, and Ashish is a student at the University of Kentucky. Roughly, the idea that we're going to talk about is error correcting codes and how they define 2D CFTs. Okay, and this is a pretty old idea. It's been known since 1990, where when Dolan, Goddard, and Montague used this idea to solve some problems in the classification of chiral 2D CFTs, which are related to classical error correcting codes. Recently, there's been some new interest in this. This in a paper in 2020, Demarsky and Shapira showed how you can actually extend this construction of Euclidean lattices from chiral CFTs, or of classical code Euclidean lattices of chiral CFTs to include quantum codes, which define Lorentzian lattices, and therefore non-chiral or full CFTs. And there's also been some other recent interesting work. So code theories, through this construction that I'm going to describe, are a subset of lattice theories, which are obviously a subset of all 2D CFTs. And because they're a subset of lattice theories, they're free, but their classification is still highly non-trivial. For example, at n, or n in this talk will be the central charge. At central charge equals 24, there's only 9 theories. At 85, or at c equals 32, there's 85, but then the number grows very rapidly. And for 48, for instance, they're still unclassified. So the general outline of the talk is that I'm going to describe error correcting codes and how they can be used to define CFTs. I'm going to give some overview of the results of the paper that I mentioned at the beginning. And then if there's time, I'll talk about some ongoing work, including quantum error correcting codes and averaging over CFTs, or averaging over codes. Okay. So error correcting codes are designed for communication over a noisy channel. You might imagine that you want to send a message to your friend, but the transmission line or whatever, it flips bits with some low probability. For instance, if p is 0.1, you don't have a 100% chance of correctly interpreting the message. And the idea is to use some redundancy in your encoding to improve your chance of correctly reproducing the message. So instead of sending 0, you send 0, 0, 0, 0, 0, or 1, you send 1, 1, 1 in this simple example, which is called the repetition code. And then you interpret the message as the closest code word. So here, if one of the bits gets flipped, you can still figure out the correct message. So this gives a 97% chance, a better chance of correctly interpreting the message. Okay. Now, the error correcting properties are not really going to be important for us in this talk. Mostly, we're only interested in codes because, well, we want to think of codes as just a collection of code words. Code words being the things that you're actually sending in your transmission, okay? So a code word is a binary vector of length n. And we'll need a couple of definitions. First of all, the Hamming distance between two code words is just the number of entries which are different. The Hamming weight of a code word is basically the number of ones in the code word, okay? Or the Hamming distance between the code word and 0. And the Hamming distance of a code is defined as the minimum Hamming distance of 2 code words. So the Hamming distance of a code is sort of telling you how far apart the code words are, which tells you how many errors you can possibly correct. Because if there's too many errors, then it will push you into a different code word in your interpretation stage. So generally, codes can correct d-1/2 the 4 of that errors, okay? For instance, the repetition code can correct 1 error, but if there's 2 errors, then you'll incorrectly get the message. And it's a general problem in coding theory to try to maximize the value of D, the amount of error correction, for a particular length n, okay? But that's a problem for coding theorists, not us. So, and I should also say there's some trade-off between more error correction and more and longer length. Obviously, if I have the 5 times repetition code, I get more error correction. I can correct 2 errors, but at the cost of having a longer code. Okay, so let's look at another example. This is the Hamming code, or the extended Hamming code, or specifically the 844 Hamming code. This is which for us is going to be a collection of 16 vectors, okay? And you can see that there's the 0 vector, there's the 1 vector, and then there's a bunch of vectors that have 4 ones distributed in different ways. And now we're going to introduce a quantity that's useful for characterizing codes. It's called the enumerator polynomial. And its purpose is essentially to characterize the weights of all the code words, okay? So the enumerator polynomial is just some polynomial whose exponents are related to the weight of each code word. And it should be easy to understand if you look at a simple example. For the Hamming code, the enumerator polynomial looks like this, because as I just said, there's 1 code word with all zeros. There's 14 code words in the middle, have 4 zeros and 4 ones, and 1 code is all 1, okay? So now we want to understand how codes define lattices. And then we'll see when we do this that this enumerator polynomial shows up first as the lattice theta function, and then from that as being related to a CFT partition function. This is the subject of construction A of Leach and Sloan from their famous paper, Sphere Packing and Error Correcting Codes. So the way that we define a lattice from a code is we embed the code in the unit cube, and then we add a bunch of lattice vectors by shifting by even vectors, okay? So the result is that a lattice lambda divided by code C is all the vectors that are equal to C mod 2, where you take mod 2 on every entry, and there's the scaling of square root of 2, which is important to get some properties, including self-duality correct. So we'll see this in a picture. So our picture will use the double repetition code. Obviously, this is a stupid code because it can't actually correct any errors, but it's useful because it's 2-dimensional. Step 1, you embed the code in the plane. So we have 2 code words, 0, 0, and 1, 1. And then we create a lattice by just shifting by all even vectors, okay? So it should be clear how this finds a lattice, and then we scale by the square root of 2. So codes define lattice as lambda, but we know that not every lattice defines a CFT. We want the CFT to be modular invariant. So we need the lattice to be even and self-dual. An even lattice has all even norms, and a self-dual lattice is equal to its dual. The dual of a lattice is the set of points whose inner product with the original lattice points are all integers. And this ensures that the CFT will be invariant under the T and S transformations respectively. Okay, so the question of how codes define CFTs is which codes give even self-dual lattices? And the answer is a doubly even code, a code where all Hamming weights are divisible by 4, gives an even lattice. And a self-dual code gives a self-dual lattice, where a self-dual code is the set of code words whose inner product with the original code words are even, or 0 mod 2. Okay. And the classic example of construction A is the Hamming code that we showed you before, gives the E8 lattice under construction A, the root lattice of E8. And actually, the Hamming code is the unique doubly even self-dual code of length 8, and the E8 lattice is the unique even self-dual lattice in 8 dimensions. Okay. Now we can say something about CFTs. A partition function in a 2D CFT can be defined as a sum over states with some exponential of the energy, or here specifically the weight in Casimir. And if the CFT has a larger group of symmetries, then these states might organize themselves into groups, and these can be expressed as characters, and then you sum over all primaries of the symmetry. Lattice theories, bosons compactified on a lattice, have U1 to the C symmetry, and you can show that the characters of U1 to the C symmetry have this form, Q to the H over C powered to the Dedekind eta function. Each lattice vector V gives a primary with this weight. So the result is that the partition function of a lattice takes this form. The numerator is the sum of the lattice vectors, and the denominator is eta. And this function is the definition of the lattice theta function. Lattice theta function is just a sum over powers of the norms of the lattice vectors. Okay. So an old result due to Berlekamp, McWilliams, and Sloan is that the enumerator polynomial is related to the lattice theta function if you do this replacement. You take the polynomial variables x1, x0, and x1, and you replace them with Jacobi theta functions. Showing this, it's not too hard. It just requires that you remember that an error-correcting code is a code is essentially an equivalence class of vectors. So the enumerator polynomial sum over code words, and then you just need to relate that to a sum over each vector in the equivalence class, and then you can see that the code words become the infinite sum.
Can I ask a question about the previous formula? Because the numerator polynomial is a very it's like a very coarse object, right? So there are many different codes which will give rise to the same enumerator polynomial. But so this lattice seems to be, I mean, naively I would say that the lattice of the code is a much, it depends on the code itself much more than this enumerator polynomial. But this, you are saying that lattice theta function basically erases most of the.
Well, the lattice theta function does erase a lot of information, right? Like you don't have information about the individual lattice vectors, only their norms. And this is sort of like the famous question, you know, can you hear the shape of a drum? Or it's related to this idea that, you know, you lose a lot of information here, and there's you know, there can also be isospectral lattices. There can be lattices with the same theta function, even though they have different lattice vectors.
Okay, thanks.
But yes, essentially both of them are coarse objects, just like the partition function. Okay. So if we want to define an invariant partition function, then it should be invariant under these two transformations, S and T, which act on tau this way.
Buona, Adriana.
Is there a question?
No, it was not a question. It was somebody not muted.
Okay. Okay. So if we want to understand, okay. So the goal will be to translate the modular transformations into transformations on the enumerator polynomial. In other words, we want to see which enumerator polynomials will lead to a modular invariant partition function. And the way we do that is we look at how the transformations act on these Jacobi thetas, defined as T squared. And it's some fairly simple formula if you divide by eta. The S transformation mixes them, and the T transformation multiplies theta 2 by I. There's this sort of annoying 24th root of unity that shows up there, but essentially by deriving these formulas, you can see that in order to define a modular invariant partition function, the enumerator polynomial must be invariant under simple linear transformation. Okay.
Is it necessary or sufficient?
It's sufficient. It's completely equivalent. Now, it's important that these transformations can also be derived from the self-duality and doubly even constraints of codes. That was done a long time ago, before anything about the relation to CFTs was known. But deriving it from modular transformations is the point of view that we're going to take when we talk about this at high school. Okay, so this is sort of the end of the introduction. Error correcting codes define lattices. A subset of those codes define CFTs if they're doubly even and dual. The central charge is equal to the length of the code and the dimension of the lattice. Because of this 24th root of unity, the CFT partition function is only really modular invariant when C is a multiple of 24, but you can still do this construction, for instance, with a Hamming code. You'll just get a partition function that's not really modular invariant. I pick up the fig. And the enumerator polynomial is related to the lattice theta function, and modular invariance implies constraints on the enumerator polynomial. Okay. So now let's talk about an application of this idea. It's possible to count enumerator polynomials that actually satisfy the symmetries. Well, it's possible to count enumerator polynomials that have positive integer coefficients and satisfy symmetry. If you look at the definition, it's clear because each term in the enumerator polynomial comes from a specific code word, it's clear that the degeneracy should be positive integer if this is really going to come from the code. So this leads to a finite number of valid enumerator polynomials. And if we do this, we'll find a number of enumerator polynomials that don't appear to correspond to CFTs. So let's look at an example. N equals 24 is sort of the first non-trivial example. So first we write down the most general homogeneous degree n polynomial. It has whatever, 24 undetermined coefficients. The first coefficient must be 1 just to ensure the partition function is correctly normalized. And then we impose modular invariance. And actually this is quite strong. It narrows this polynomial down to a single undetermined coefficient. And you can see from the form of this that if we impose that all the coefficients are positive integer, we just get a simple inequality for A4. And this means there's 190 valid enumerator polynomials. Now, when I say valid, if you expand these in Virasoro characters or you want to the C characters, they'll have all positive integer coefficients. If you just look at this and think of it as a partition function, it's, as far as I can see, it's impossible to tell that it's not valid. But we can compare this because in C equals 24, these things have been usefully classified. There's only 9 doubly even self-dual codes. There's 24 even self-dual lattices. These were classified by Zoominar. And there's 71 chiral CFTs total, according to Shellikins. So the question we want to address here is, what are all these extra partition functions? And I should say that the same problem exists for quantum codes, which define non-chiral CFTs. And this is actually, this was pointed out by Demarski and Shapiro, and this is actually what got us interested in trying to use this higher genus approach in the first place, to try to say something about the CFTs, or try to say something about whether these are CFTs. And I'll spoil the answer. We weren't really able to show that they're not CFTs. We derive an algorithm that shows that they can't possibly be error correcting codes. So, okay, I'll explain that a little bit later, but this was a lot of the motivation for what we're going to do in this section. Okay, so let me take a brief pause and see if there are any questions. Okay. And feel free.
Yeah, I guess I'm not 100% sure. So there was a lot of stuff. So you are saying that this is an enumerator polynomial, but one enumerator polynomial corresponds to many error correcting codes. So
well, in practice, these codes are quite sparse. I mean, there's only 9, and all of these codes have different enumerator polynomials. The set of doubly even self-dual codes is not that large. You could, if you just want code, you just want collections of vectors, then of course there's a huge fix. But these structures are, yeah. Okay, there's a pair of isospectral codes at C equals 16, which are related to the 16-dimensional isospectral lattices, but generally they're not, the doubly even self-dual ones are not going to be dependent. I mean, I don't know what happens at C equals a million.
But so, yeah, but for example, this extra enumerator polynomials, could you just address your question by showing that the extra enumerator polynomials don't correspond to any DESD code?
Well, in practice, it's not clear how to do that.
Okay.
If someone gives you an enumerator polynomial, or like I mentioned this at the beginning, but these codes are classified at C equals 24, C equals 30, and C equals 32 and C equals 40, but at C equals 48, there's already too many. So if someone gives you a code, you don't have a enumerator polynomial, you don't have a list to compare to.
Okay.
It's kind of like if someone gave you a modular invariant function and said, tell me if this is a CFT or not. Until you've classified them, you don't know how to do it.
Okay.
Or maybe you have some
Okay, sounds good.
Okay. So we want to try to understand the constraints that come from higher genus modular invariants. So let's briefly review. At genus 1, partition functions only depend on tau. Conformal transformations can map any torus to the flat torus, and the remaining Riemann surface only has one undetermined complex parameter. At higher genus, the generalization of this is called the period matrix, and it's defined this way. We choose a basis of cycles where the intersection numbers are delta between A and B are delta functions. This is just obviously a genus 2 example. Genus G surfaces will have G independent holomorphic 1 forms. And then the conformal transformation can be used to normalize the integrals along the A cycles to be 1. And then the remaining integrals specify the period matrix of the surface, which has the property that it's symmetric and positive definite. The imaginary part is positive definite. And this is the direct generalization of genus 1, where the natural 1 form is just BZ. The A cycle is the line from 0 to 1. The B cycle is the line from 0 to tau. And then it's clear that if you integrate omega 1 over B, you get tau. So the only period matrix entry in genus 1 is tau. And the group of transformations that act on the period matrix but leave the surface the same is the higher genus modular group. And this group is the symplectic group 2G. Okay, these are 2G by 2G matrices with entries, with integer entries. Okay, so we want partition functions that are invariant under this transformation. And for a theory on a lattice, the higher genus partition function takes this form. It's going to be a higher genus lattice data function, which I'll talk about more, divided by this denominator, which is roughly analogous to the generalization of the C powers of the Dedekind eta function. So the denominator, in higher genus, there aren't any closed form expressions. It's not really going to factor into this talk because it's theory independent. So we're going to be focusing on the numerator, which is the higher genus lattice data function. So a higher genus lattice data function is defined as sums over G tuples of vectors this way. So this formula is a little confusing because this vector V is what has an index.
So I didn't understand. What does it mean that it's theory dependent? Because I saw that the numerator depended on lambda and the denominator didn't depend on the theory, just depended on omega. So why do you say it's theory?
Theory independent.
Theory independent. Okay, sorry.
So this is a sum over G tuples of vectors, and these vectors have indices that run from 1 to G, but they're also vectors of length n, where n is the length of the code, or but it's a little simpler to see at genus 2 that you just sum terms with each of the entries of the period matrix, and you just sum over every possible pair of vectors in the lattice. And what we discussed in the paper is that this is actually related to the higher weight enumerator polynomial, which is an object that's not as commonly studied in the coding literature, but which has also been known for a long time due to McWilliams, Mallet, and Sloan. The higher weight, or the weight G enumerator polynomial, is likewise just a sum over G tuples of code words. So before I just had n and the weight of a particular code word in this exponent, but now I'm taking dot products of code words as well. And here I just wrote the genus 2 version because the higher genus generalization is more complicated. Basically, there's no obvious way to take a dot product of 3 different code words. So the way we do it in the paper is we use the logical and symbol, but I think, yeah, so the genus 2 version is much simpler. And now we want to do something directly analogous to before. We want to replace all of the code variables with these higher genus data functions. And we find a result that the higher weight enumerator polynomial is related to the higher genus lattice data function. Okay. Okay. So I should point out this was known in this paper by Runge, which was about the relationship between error correcting codes and modular forms. Actually, we found a lot of what we did was already known from sort of a different point of view, especially this paper, which we'll show up again. Okay, so now we want to translate the constraints of higher genus modular invariance into constraints on the enumerator polynomial. Now, the higher genus modular group acts on the period matrices in this way. So it's analogous to how they act on tau. Tau goes to A tau plus B over C tau plus D, but now A, B, C, and D are G by G matrices. And at genus 2, this symplectic group is generated by 3 matrices. Here's one choice. So from this, you can directly read off how these transformations act on the theta functions. And from that, you can figure out how the modular, using the Poisson summation formula, you can figure out how the modular transformations act on the code variable. Okay. And
excuse me, I have a small question. These modular transformations, do they have any meaning in the information theory side of the problem?
Oh, you mean?
I mean, you're talking, it's supposed to be some correspondence. So are like people that do code correction, classical code, are they interested in such transformations? Is it a natural thing for them, or it's artificial correspondence?
Yeah, sorry, I just got a note to try to switch on and off the mic. I don't know if you can still hear me. So yeah, the higher genus modular transformation, okay, at genus 1, modular transformations came from the requirement that the code is doubly even and self-dual. So to answer your question, yes, they do. Essentially, you want to think of the, for instance, at weight 2, you can think of the weight 2 enumerator polynomial. Well, this is actually the specialization of something called the joint weight enumerator polynomial, where you sum over code words of 2 different codes, and then you sum over pairs of code words of 2 different codes. And then you can see that the doubly even self-dual property of 2 different codes will imply some constraints on the joint weight enumerator polynomial. And that simplifies a lot when you say that both of those codes are the same thing. So essentially, I want to think of them as arising from the doubly even self-dual property of the codes. And I think of summing over code words of 2 copies of the same code. Okay. I don't know if that completely answers your question, but the short answer is yes. So, okay, so these formulas, which we derived from modular invariance, but which can also be derived and have been derived from just looking at the codes themselves. I think the interesting thing about them is that they're just so much simpler than the modular transformations as they act on tau because they're linear. So now we're going to see how we can use these to count the genus 2 modular invariant partition functions. Okay. So remember we had $190 enumerator polynomials at genus 1. What happens at genus 2? So first, again, we write down the most general polynomial. It's a homogeneous degree n polynomial of 4 variables. And we impose genus 2 modular invariance, which gives a very long invariant polynomial, but it actually only has 2 undetermined coefficients. And imposing that these coefficients are positive integers implies a set of inequalities, these 5 plus like 10 more or something. And if you count, there are 165,035 possible solutions. Okay. So that's not so useful, but we need to impose something else, which if you have thought about these genus 2 partition functions, you may have already guessed, that's the factorization limit, which is that the partition function should factorize into the product of two lower genus partition functions in the limit where they're just attached by a point or an infinitely long thin tube. Okay. Now we can impose this by just looking at the genus 2 partition function in a limit where omega 1, 2 goes to 0, in which case omega becomes diagonal, or for higher genus case, you want to set a whole set of off diagonal parts to 0, and then omega will become block diagonal. And by looking at the Jacobi thetas, we can see exactly how this acts on the code variables. The 4 code variables of the genus 2 go to each possible pair of code variables of the genus 1. And we find actually that only 29 enumerator polynomials obey this constraint. This 29 is a subset both of 165,000 and of 190. What I mean is only 29 of 165,000 genus 2 polynomials factorize, and they factorize into a subset of 29 genus 1 polynomials, a subset of the 190. And as a good check, this list includes all 9 of the codes. You know, the theories that actually come from codes. So our conclusion is that the higher genus constraints reduce the number of fake polynomials. Okay.
In the sentence where you say this includes all 9 of the codes, you mean those that also obey self-duality?
Yeah, that's right. So
thanks.
Yeah, so Conway showed that there are exactly 9 doubly even self-dual error-correcting codes of length 24, which is part of the reason it's nice to do this at c equals 24. And we can see that all 9 of them are on our list of 29. So our list of possible codes went from 190 to 29. Okay.
And so the idea is that if you continue cranking up the genus, you might reduce to exactly 9?
That is exactly the idea. So actually we did this at genus 3, and we get 21. The genus 3 polynomial, even the invariant polynomial already has 7,000 terms, so it grows very fast. Practically speaking, we don't have much hope of doing it at genus 4 with our method. Maybe there's some clever generalization. So, okay, here's just a diagram of all of the codes on the right, all of the lattices in the middle, and the codes for the list of things that polynomials that still exist when you use genus 2 and genus 3. And K here is directly related to the number of currents. The number of currents is 24 times K. Okay. So you see that like when you go to genus 3, you chop off all these guys. You still have this one, which is the last code, but you still have a bunch of bad ones in here. And you also see that our method is killing lattices which are not code. And it also might be interesting to look at the distribution of enumerator polynomials. So as I said, at genus 2, there's only 2 indeterminate coefficients, so we can plot it easily. And the constraints that I showed actually give you a nice finite region. Honestly, it had to be finite since it had a finite number of solutions. And if I counted all the integer points in this graph, then I should get 165,035. And then you can ask, where do the 29 factorizing ones live in this? And this is where they live. So obviously it's a very small subset. Actually, this is just the series of 190 that keeps going outside this region, and the ones inside the region are the ones that we keep. We also kill one down here, which I get. This one. Okay, so let me say some of my conclusions from this section. The first conclusion is the fake enumerator polynomials cannot be code theories. And actually, we found after doing this that this number 29 was already known from the code point of view by Runge. So it's a little disappointing when we saw it, but okay, that's how it goes. So I would phrase our result as a sort of translation of this method into a sort of CFT-centric point of view. Now, this paper also has another very interesting observation, which is that if you go to high enough weight, the enumerator polynomial will completely fix the code. In other words, you can just read off the code words from the degeneracies of various terms. Now, the weight is for a doubly even self-fill code, it's n-1/2. So for the C equals 24 code, you need to go to weight 11. That's obviously much higher than you can do in practice. But the conclusion is that code theories are completely characterized by higher genus partition functions. In other words, if you told me the definition of a code theory, then I could do just that. I could impose modular invariants at each genus, and eventually, once I get to this genus, or hopefully some lower genus, then I can completely just read off the theory from enough partition functions. Okay. And I think the power of this, as I said before, comes from the fact that code theories have partition functions that can be written in enumerator polynomial form. In other words, the constraints of modular invariants are very simple. Now, for chiral CFTs, actually, it turns out every theory can be written in enumerator polynomial form. For instance, all of the 21 theories classified by Shelkins have a numerator polynomial form, but the ones that are not codes don't have positive integer dependencies. I'll say a couple words about the case of non-chiral CFTs where I don't think that's the case, but I don't know. I think it's possible that this enumerator polynomial form could be useful beyond code CFTs. That's speculation. Okay, so one thing that we didn't do is we didn't show that these fake things were not CFTs. Now, in the case of C equals 24, we kind of know they're not CFTs because they're not classified, or because the CFTs are classified and they're not on that list. But if someone handed you a CFT, you wouldn't be able to tell it's not a CFT by doing it. You would only be able to tell that it's not a code theory. So now this problem also exists in the quantum case. So maybe this could be, maybe one way of attacking this could just be the traditional modular bootstrap. You have this fake partition function, you just write, you can easily extract a spectrum, and then you could just try to understand if it's real from that point of view. Another interesting thing would be to try to generalize the procedure to find general lattice theories or general chiral theories. And another thing that we're kind of interested in is trying to extract the OPE coefficients. One of the results of this is a lot of explicit genus 2 partition functions. So it'd be interesting to sort of play around with what are the OPE coefficients of the ones that factorize or don't factorize, or does that question even make sense? So yeah, so that's something that we're interested in the future. Okay, but in my remaining time, let me just summarize a little bit 2 follow-up projects I'm doing. And the first one, also with Johan and Ashish, is extending the story to quantum error correction codes. So as I said at the beginning, this old construction A story was recently given a quantum version by Demarsky and Shapiro. And instead of 2 to the G variables, here we end up with a lot more variables. So Genus 2, we already have 10. And we can do the same algorithm. For instance, at C equals 3, there's 6 fake theories. And we find actually at Genus 1, but we actually find that Genus 2 completely fixes everything and converges immediately to the set of codes. At C equals 4, you end up with 1 fake theory. I think at C equals 5, there's 2 fake theories, and then you start getting more and more fake theories as you go up. And other questions that we hope to address, what's the relation between invariant polynomials and modular forms? So I didn't talk that much about the modular form story, but it's actually a pretty big part of our paper. And that's because it's known that there's a close relationship between the error correcting code, enumerator polynomials and modular forms. But if there's any such relationship or what the nature of that relationship is, it's completely unclear for this generalized, this quantum construction A. So it'd be interesting to do that. We've classified the ring of invariant polynomials, and it has a finite number of generators. I don't think modular forms do, although I'm not sure. So that would be something to explore. Another question would be to try to maximize the gap, assuming a numerator polynomial form. So this enumerator polynomial form is a really simplifying ansatz for a partition function. And it'd be interesting to sort of see if you do this and then try to do some sort of traditional modular bootstrap approach, then what you can see. And just more generally, it'd be interesting to look at other constructions. So I mean, the space of quantum error correcting codes, I didn't say this, this is just a small subset of the quantum. These are called the stabilizer codes where they did this. But this set of quantum codes is much richer than the set of classical codes. So potentially there's a lot more to be understood in that. Okay, so now I want to talk about the other follow-up that I've been doing with Johan, and that's the story of averaging over codes. So first, I'm sure many of you are aware, there's been some interesting developments in averaging over lattices, especially these 2 papers from 2020. And there's a chiral version of this story where if you sum the lattice data function over weighted by the number of automorphisms, then you get the Eisenstein series times some rational number. Now this story is for full CFTs or Lorentzian lattices. So these have a continuous moduli space. The Euclidean story is much simpler, and you're just summing over a finite number of things, or a discrete set of lattices. And there's actually a version of this formula for error correcting codes. It's almost exactly the same. You sum the enumerator polynomial weighted by the code automorphism, and it gives you the average code, or the average enumerator polynomial times some rational number. And the average enumerator polynomial has this form. Okay, it's a fairly simple function. It's different, obviously depends on the charge. So we've been playing around with this recently, and the first thing you might do is just look at some of these average partition functions and just try to see what you can understand. So for instance, we can expand some of these things at small q. We should see some things that make sense. At c equals 8, there's only one code, the Hamming code. The Hamming code is related to the E8 lattice, which obviously has E8 symmetry. So this thing has a hugely enlarged set of currents. But then as you increase the central charge, you actually find something interesting. This average partition function seems to be converging to something with 3 times the number of, where the number of currents is 3 times the central charge. Okay. I say partition function in quotes because I don't know if this is a real theory or anything, just kind of playing around with formulas. But a natural guess is that maybe this could be related to SU2 because I have 3 currents per central pipe. And you can look up some formula for the SU2 characters for level K and weight H. And actually for K equals 1, you find something really interesting, which is that the characters, there's only 2 non-zero characters, and they're actually related to theta 3 and theta 2, which we had before. So what this means is that the degeneracies of code words actually are degeneracies of SU2 characters. If I had known this sooner, then I would have put this probably at the beginning of my talk. But so recall that our map from enumerator polynomials to partition functions essentially replaces x0 with this function and x1 with this function. So the degeneracies in front of these polynomial variables are just these SU2 character degeneracies. Okay, so we have some sort of, again, preliminary, but some guesses of what's going on here. Our procedure for finding code theories is actually looking for SU2 degeneracies. And we think that where this SU2 comes from is the U1 to SU2 enhancement that happens in string theory when you compactify the self-dual radius. We think that it's directly analogous to that. It sort of makes sense because error correcting codes were sort of the subset of lattice theories where all the generators could be embedded in the, defined by the unit cube. So all the generators of the lattice have a particular length. So this is why we think we're getting this SU2 enhancement. So a natural question would be, is the space of these SU2 theories the same as the space of code theories? And I should also point out, actually in 2020, Maloney and Witten already realized that this would happen if you had some symmetry enhancement. They talk about the symmetry enhancement from one U1 to they have some U1 to the C theory, and they talk about enhancing one of the U1s, and they say that you'll change the characters from 1 over eta to theta over eta. So our claim is that actually the code theories are the theories where you enhance all of the U1s to SU2. Okay, so let's go back to the average theories for a minute. First of all, we have 2 characters. X0 has a lower weight than X1, which means that the lowest weight character is basically X0 to the n. And we can try to understand what is the gap in SU2 characters. The gap is roughly where the degeneracy and the density of states is roughly equal to 1. And you can see, for instance, by picking some random large number, that first you have a coefficient 1, and then you have really, really small numbers, which I guess are going to 0 in the large n limit. But the numbers grow, and then eventually they get bigger than 1, and then they blow up and get very big. And it appears that delta gap, the gap in SU2 primaries, is C over 36 point something, or the solution to this equation. And you can compare this with the lattice gap. For chiral theories, the gap in U1 primaries is exactly this number. It ends up being about C over 34. So the SU2 gap is a little bit smaller, but okay. And a final comment is that you can actually do this sort of sum over modular images story, which is used in the gravity case to try to understand the partition function of quantum gravity. In the case of these code theories, it's extremely simple. X0 to the n has only 6 unique modular images. It's just all of these polynomials. And this is exactly, the sum of these is exactly the average numerator polynomial up to this factor, which goes to 1 in the large n limit. So we think we don't need to worry about it. Okay. Actually, the sum over images trick is very useful, and we were able to use it to find the average genus 2 or genus 3 enumerator polynomials. Or I should say, we guessed the average and then we checked it for equals 24. So I think it's right.
Can I ask a question?
Yeah.
Can you hear me, first of all?
Yeah.
Is this just the same sense in which chiral CFTs are fixed by their polar part? By polar, I mean the part that diverges as you take, say, q to 0.
Yeah, sorry.
Like, does chi0 give?
Sorry, go ahead.
Oh, sorry, but here maybe.
Well, okay, I'm not exactly sure, but I can say one thing, which is every code theory has the same first term. But when you average over all of them, that's when you get this.
Yeah. Should I? And I should be thinking of that as like the vacuum character.
Yeah, that's our.
With respect to this bigger chiral algebra.
Yeah, exactly. Yeah, that's our interpretation.
Okay. All right. Thanks.
Yeah. So okay, I mean, okay. So I'm basically done. Our speculation is that this is some SU2 version of the U1 gravity story. We're still trying to understand this, and kind of new for us, or trying to understand what it would even take to show that. And the more general question is what's the non-chiral version of the story, or maybe there's even more than one non-chiral version of the story. So that's something that Johan and I are excited about exploring more in the future. And okay, I think I'll end there. So thanks for listening, and if there are any questions, feel free.
Thanks, Brian, for a very nice talk. Are there any questions? So I have a question about this average code polynomial. So you are saying that this conjecture that you are making about U1, that every U1 enhances to SU2, it should be true in some average sense. Like, okay, there's some theories out there which do not have this enhancement. So what's exactly?
No. Okay. Yeah. Sorry.
Yeah. How you?
Confusing because I stopped talking about the average at some point. Basically, what we found by looking at the average is that the average theory has its SU2 symmetry.
As what?
This leads to a more general statement. Because the SU2 characters are actually just x0 and x1. So actually, every code theory has this SU2 symmetry. Because
Just a conjecture, can you check, for example, that some theories that have been fully known, like the one at center charge 8, can you check that it has SU2 symmetry?
Well, yeah, that's a good question. I think.
Well, it's like a zeroth order question.
Well, the zeroth order question is that we know that its partition function factorizes into SU2 characters. And yeah, and the next question would be to sort of understand if this is really what's happening. If you can look at the code words, you can look at the lattice and see that this symmetry enhancement is happening. So, yeah.
Okay, so you have a conjecture that every of these code theories has SU2 symmetry, but then you're also making another conjecture which was related. So this conjecture is not related on averaging; it's just. Yeah, this conjecture. But then there was some part of the conjecture which was related to the form of the average polynomial. So what was that?
Well, yeah. So I don't know. Maybe conjecture is too strong, but yeah. To us, based on this delta gap scaling with C and In particular, yeah, I guess we conjecture, we're guessing that this is some SU2 version of the average story. So these code theories are sort of like the subset of lattices where all the U1s get upgraded to SU2 because they have like particularly defined lengths of all the compact directions. And then that would lead to a case where you're actually just, you're not averaging over all lattices, you're only averaging over a subset, a very small subset in the large C limit that have this enhanced symmetry. And, okay, we don't know if that's true.
But what's your interpretation? So some of these average coefficients, they're very small below the gap, but non-zero. So it means that there are some code theories which do not have a large gap. Very rare, but there are some code theories with very small gap.
Yeah,
How do you interpret
that? That's the same thing that happens for
those do not look like gravity.
Okay, so yeah, so I look. Okay, maybe this is the best thing to look at. This is some large value, but it's not infinity. It's not C equals infinity. So this number gets even smaller if I increase this number more. And you can do the same thing for the lattices and you see sort of the same pattern. Basically for finite C, then you get that the first coefficients are extremely small, but then eventually they become order 1. And the place that they become order 1 scales linearly with C.
No, absolutely. But the theory of gravity would have a large gap even at finite C. So something
okay, well,
that's
that's
not quite.
Case, I don't think it would work exactly for the lattice, for the average of the lattices either. But yeah, okay, I guess I don't know.
Okay. Any questions from the audience?
Yeah, I have a very simple question, Brian. Very nice talk. So what is the relevance in the error correcting theories of the self-duality of the lattice?
So, yeah, so by looking at the definition of a self-dual lattice and a self-dual code, you can see that those are equivalent conditions when you impose construction A on the code. In other words, a self-dual code leads to a self-dual lattice under construction.
Yeah, but I mean, the quantum information or the error correcting features that I don't know about. Is there any relevance about having this self-duality, or
that's a good question.
Do they play any role, or?
Yeah, I don't know. Yeah, the self-dual codes are studied. Yeah, I don't know.
Okay, thanks.
Any further questions? Well, if no more questions, then thanks again, Brian. It was a very interesting subject. So bye, everyone, and see you next week.